Good day, students. Welcome to mathgoodserve.com. In this clip, we're going to be going over another example on optimization and modeling. Do not forget to visit our website at mathgoodserve.com for access to a wide variety of tutorials ranging from algebra all the way to calculus. So these are the 5 steps we're going to be using to solve our optimization problems. Step 1 is modeling, where we will create a diagram where applicable, generate an optimization and constraint functions. Step 2 is substitution, where we'll have our function in terms of just one variable as a result of substituting our constraint function into our optimization function. We will also state the domain in step 2. In step 3, we'll go ahead and find our potential extremas, which are the endpoints if the interval is closed, and our critical points. Step 4, we'll go ahead and determine which of those critical points yields our extrema, and then we'll verify our result using the second derivative test. Lastly, we'll state the meaning of our solution within the context of the problem. Alright, so this is the problem we are solving here. Question number 6 says Vanessa desires to build a rectangular fence to house her pigs and chickens in her new mansion. She desires to have the pig and chicken pens adjacent to one another with equal areas in such a way that they share one common fence. What are the dimensions of each pen that will enclose the biggest possible area if she has only 400 feet of fencing? Okay, so the 5 steps are placed on the side right here for a reference. Step number 1 is modeling. Let's see if we can create a model of this situation. Alright, so let's go ahead and draw what the fence looks like. So we have a rectangular fence. So let's say something of this nature. A little bit smaller. And the rectangular fence is split into 2 equal halves. So something like this. So this is the rectangular fence. So let's say this is for the chickens and the other is for the pigs. Okay, how about we call the adjacent sides x? So x, x, x. So these represent the length of our rectangular fencing region. All right, and then let's call this the width. I don't know what that is yet. Okay, so how much material do we have to build up this fence? She has 400 feet of fencing, so this entire length is going to basically be 400 feet. So let's divvy it up. So from here all the way to here is 400 feet. Okay, now from that 400 feet we're going to basically break it up into this rectangular pen that's existing here. Okay, so this is 400. Now what we're doing is we're taking 3 equal side lengths to represent the length. So let's call this 1, take the first one, second one, and third one. So this is x, x, x. So this side right here is this side goes to the middle, and this side goes to the leftmost side. All right, now if you take away 3 x's, that means this entire length right here is going to be 3x, and it basically represents the measure of the adjacent side. So this is 3x. Now if the entire fence has a length of 400, then how much length do you have left for the top and bottom sides, the north and south sides of the fence? The entire thing is 400. We've taken 3 x's for these 3 sides right here. So the top and bottom together should be the entire length, which is 400, minus the three sides. Okay, so this side right here has to be 400 minus 3x. Alright, so 400 minus 3x is for the top and bottom. But what are we doing here? We have to split it down the center to get the measure of the top and the bottom of this rectangular pen. Alright, so there goes the middle of the 400 minus 3x. So this side right here represents the entire top, and this side represents the bottom. So if this is 400 minus 3x, then what's the measure of each side? All we simply do is we just take 400 minus 3x and split it into 2 equal halves, and that will tell us the measure of each side. Okay, so let's go ahead and do that. So we have, I'm going to change the color here. The top is going to be 400 minus 3x divided by 2, and then the bottom is going to be 400 minus 3x divided by 2 also. Okay, so based on this setup, we know that our width is going to be 400 minus 3x over 2 on the bottom, and then also on the top is also 400 minus 3x over 2. If you combine all these side lengths together, you should end up with 400. Alright, so now we have the graph set up. Now our area, our area is going to be, well, let's label our functions in a manner consistent with our setup here. So we need the optimization function. So optimization function is what we are maximizing or minimizing. Okay, so what's the optimization function here? We have to go back to the problem. The problem says find the dimensions of each pen that will enclose the biggest possible area. So we optimize an area. Okay, so what's the area of a rectangle? Area of a rectangle is length times width. All right, and then we also need our constraints. Our constraints are the constraints on the sides. We know that if we say the length is x, then the width must be 400 minus 3x over 2. All right, so there goes our optimization and constraint functions for part number 1. So we have that done. Now let's move on to part 2, substitution. We want to write down our optimization function in terms of just one variable. Okay, so part 2, substitute. Now, since we know that area is length times width, and as we see in part 1, length is x, width is w. The values of, width is 400 minus 3x over 2. We can substitute these two values here. So our area in terms of just the variable x is x times 400 minus 3x, that divided by 2. Alright, so I'm going to simplify this function so it's easy to differentiate, but we also have to state the domain. Okay, so if I simplify this function, I'm going to have 400x over 2 minus 3x squared over 2. So our function is going to be 200x minus 3 over 2x squared. Now we also have to state the domain. How small can x be in this situation? Well, the x could be 0. In that case, we'll just have 200 and 200 for the north and south sides of the rectangular fence. So the lowest x could possibly be is 0. 0 less than or equal to x. Now how big can x get? We can easily find out the constraint on x by looking at the width. The width cannot be negative, okay, because as x gets increasingly large here, we can see that this number gets smaller. So since the width um, let's put this in green. Since the width has to be greater than or equal to 0, that means that 400 minus 3x over 2 must be greater than or equal to 0. If we solve this, we'll have 400 minus 3x is greater than or equal to 0 by multiplying both sides by 2. And we subtract 3x from both sides. We have, if we add 3x to both sides, we have 3x is less than or equal to 400. Because if you move it over here and you switch the inequality, switch the order of the inequality, we have 3x less than or equal to 400. Divide both sides by 3, x is less than or equal to 400 over 3. Okay, so our upper constraint on x, 400 over 3. All right, so we have the function and the domain. Next, part 3, we want to find the extremas. The extremas are our critical points and endpoints. All right, so step 3, we want to find the extremas. Well, to be precise, we're looking for potential extremas. Potential extremas. And the candidates that we're looking at are our critical points and endpoints. Okay? That's what forms our potential extremas. Okay, let's find the critical points first. What are your critical points? Your critical points are where the derivative is equal to 0 or the derivative does not exist. Okay? So those are your critical points. We have our function is 200x minus 3 over 2x squared. Now if you take a look at this function, does this function have any vertical tangents, corner cusps, or discontinuities? The answer is no, because this is a parabola, right? A downward facing parabola, which means that the derivative is defined for all values of x. So there are no points where the derivative is non-existent. Okay, so let's keep that in mind. But let's just differentiate just to make sure. So if we differentiate this function, a prime of x is equal to 200 minus 6 over 2x. Okay, and then that simplifies to 200 minus 3x. Now, to finish this off, we'll just set it equal to 0. 200 minus 3x equals 0. And then when you solve that, 3x is equal to 200, and x is equal to 200 over 3. Okay? Now, when is 200 minus 3x undefined? When is it undefined? This is a linear function. It's defined for all values of x, so the answer is never. This function is always defined. Okay? So since the derivative is always defined, that confirms our conclusion earlier that the function is differentiable for every x in the domain. Okay, so this is our only critical point. So our potential extremas that we're going to declassify momentarily, potential extremas are x equals 0 for the lower bound, 200 over 3 for the critical point, and 400 over 3 for the upper bound on our domain. Okay, now let's move on to step 4, where we're going to classify. Go ahead and do that, classify. Alright, so to classify, what we'll do is we just plug in these potential extremas into the area function to see which yields the largest result. Okay, so a of the lower bound, let's recall what a of x is. A of x is 200, let's see, a of x is 200x minus 3 over 2x squared. Sorry, a of 0 is going to be 200 times 0 minus 3 over 2 times 0 squared. If you work this out, you get 0. A of 200 over 3 200 over 3, that's a critical point. We have 200 times 200 over 3 minus 3 over 2 times 200 over 3 square. And then we have 4,000, no, actually 40,000 over 3 minus 3 over 2 times 200 square is, let's see, it's 40,000 over 9, right? 3 goes here 1, 3 goes here 3, 2 goes here 1, 2 goes here 2, 20,000, right? Okay, and then if we work this out, we will get 20,000 over 3. So 20,000 over 3. Remember, these are areas, okay? So this is feet square. This is feet square. And then if we do A of the upper bound, 400 over 3, we have 200 times 400 over 3 minus 3 over 2 times 400 over 3 square. If you work that out, you get 80,000 over 3 minus 3 over 2 times, if you multiply for 400 by 400, you have 160,000 divided by 9. 3 goes here 1, 3 goes here 3, 2 goes here 1, 2 goes there 80,000 times, and if you subtract these two, you get 0 feet square. Okay, so we can see that the biggest is A of 200 over 3. Okay, so largest is A of 200 over 3. All right, we're going to use the second derivative test for confirmation here. So what's the second derivative of our function? A double prime of x is the derivative of the first derivative. Remember, 200 minus 3x was the first derivative. So when you differentiate this, you end up with negative 3. All right? So A double prime at the critical point is negative. Is negative. All right? So that's what we care mainly about. Okay, so what does this tell us? Using the second derivative test, since A prime of 200 over 3 is equal to 0, which makes it a critical point, and A double prime of 200 over 3 is negative, what does that imply? Then A of x is concave down. It's concave down, hence A of 200 over 3 is a maximum. You know, if you have a downward facing concavity at an extrema, that point is in fact a maximum. All right? Okay, so there goes our classification to go ahead and finish this off. All right, so for part 5, let's go ahead and state our conclusion. Part 5, conclusion. Let's basically state what the meaning of our answer is within the context of the problem. So we know that our length is x, which is the x that we found, 200 over 3. And then our width is 400 minus 3x over 2. So we're just going to plug in this x value here. So that yields 400 minus 3 times 200 over 3 over 2. Okay, so this cancel out. We'll have 400 minus 200, which is 200 over 2, which is 100 feet. All right, so that's the width of the entire fence. Okay, so entire width is 100 feet. but we are dividing the entire width into two, into that of the chicken and the pig, right? So the individual width of each pen is going to be half of the entire width, so 100 over 2, which is 50 feet. Okay, let's take a look at the problem real quick so you understand what I'm talking about. Now, the entire width from here to here is 100, so that means this has to be 50, and this has to be 50. Because the problem asked for the dimension of each pen. Remember, this pen is composed of two pens, right? Together, their width is 100, so individually the width is 50 feet. So in conclusion, the dimensions of the individual pens that will yield the maximum area and we know what that maximum area value is, which is 20,000 20,000 over 3 feet square. We got that when we're doing our classification. Where was that? Right here. See this one? That's the maximum area. So the dimensions of the individual pen that will yield the maximum area of 20,000 over 3 feet square is 200 over 3 feet for the length by 100 feet. Oh, sorry, 50 feet. Okay, by 50 feet. So that's the width of the individual pen. Okay, so that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. If you have any questions about this lesson or you would like to request videos, feel free to include it in the comment section below. More clips can be found on mathgoodserve.com. Thanks again for watching and have a wonderful day.